Good. So good afternoon, everybody. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are particularly excited this April because all month long, we are showcasing climate research and climate change. And that's all being made possible by Environment and Climate Change Canada, who are sponsoring our entire month dedicated to this topic for the first time ever in April. So we want to say a huge thanks to them. Right now, we're joined by 5 classes from across North America. I'm going to give them a chance to do a bit of a shout out, and then we'll dive right in. We've got Miss Rendine's grade 4s in Dover, New Jersey. Hi, guys. Hey, and their mic's muted again, but they're excited. We got it working. It's not working anymore. It'll figure it out. Cool. We've got Miss Caesar's grade 6s in Prince George, BC. Hi, guys. Hi. Hey. We've got our Miss Rendine's class. Perfect.
We're back. Say hi.
You're back. Okay, we've got Miss Fletcher's grade 5s in Mount Airy, North Carolina. Hi, guys. Hey! Hey! We've got Mr. Gohar's grade 3s in Bernie in Texas. Hi, everyone. Let's get that. Hi, guys. They're excited too. Some of you guys might need to demute your mics at the end. That's totally fine. I'll let you know when we get there. And then last but not least, just joining us a second ago, we've got Miss Carton's grade 4s in Anchorage, Alaska. Hi, guys. I honestly don't think you go to any classes. You just do Exploring by the Seat of Your Pants hangouts, and we appreciate it. Of course, the reason you guys are all here today is for our speaker. So we are joined live at MIT by Henri Drake, who is a graduate student jointly between MIT and the Woods Hole Oceanographic Institute, 2 of the most elite research centers in the entire world. And what he does is work on the circulation of water in our oceans and how that contributes to global climate change and how that contributes to our global climate system. So without further ado, I'm going to turn it over to Henri. Thanks so much for joining us, and we look forward to hearing all about your work.
Yeah, thanks for the intro, Jesse. And I'll start off with a little PowerPoint presentation. So I put together some movies and some figures that explain my research. So without further ado, let me get started. All right, I'm going to share my screen. Okay. So oceanography and climate science, the way I like to think about this is really it's making math beautiful. So this is a picture, and now it's a movie. And this is really our best understanding of what the ocean looks like today or over the last 10 years. And so this is a combination of measurements, a computer model, and there's maybe 100 scientists at NASA and MIT who work together for a dozen years to put this together. And what we do is, what we really want to know in climate science is how can we predict the future and how can we understand the past of the planet? So what we do is we use computer codes, lines of programs written on computers representing a bunch of equations, and we use those to predict things like global warming. So what's shown here on the y-axis is temperature. This is the average temperature of the entire planet. And on the x-axis is year, starting in 1900, so about 120 years ago, going all the way to 2100, so in about 80 years. And the black line here is showing the increase in global temperatures over the last 150 years, 120 years until today. And so this spike here, you see the largest of the black line, values of the black line, was in 2016, which was the warmest year on record. And then it's gotten a little bit colder since then, but it'll probably shoot right back up next year. Okay, and so what I'm showing in the blue and orange lines, these are predictions of future global warming that we use from computer models. So obviously the future hasn't happened yet, so we don't know exactly what will happen, but we can say, unless we change the way society works, unless we stop emitting greenhouse gases, we are going to follow one of these 2 lines. The blue line is if we switch a little bit away from fossil fuels and greenhouse gases, and if we start deploying renewable energy sources, we'll follow this blue line. If we're really aggressive and we deploy a lot of renewable energy resources, we could really follow more like this red line, or maybe just stay flat and not increase the temperatures too much. And then this orange line is sort of a worst case scenario. If we just burn all of the oil, gas, and coal on the planet, and don't use any renewable technologies, we're going to have a global warming of about 3 degrees since 1990 or 3.5 degrees since 1900. And so you're here today in 2019, And you could end up here, but you really don't want to. So we'll get back to that later. But the real question, or sorry, let me now describe how these computer codes work. So the way that we build these computer codes is we take part of the planet. So this is a version that was developed in New Jersey at the climate lab there. So if you take part of the planet, that's this square here, about the size of New York City, and we break the planet up into a bunch of squares, all that size, and we do that for the entire planet, right? So here is now, let's see, this is, I guess, Long Island, and I'm up here, I think. That was New York City. And if we break up the whole planet into these boxes, then we can use equations in our computer programs to describe how water and heat and salt and nutrients and all kinds of things move from one box to another. Not just today, but also in the future. We can run these models forward in time to predict the future. And so this is what that looks like when you start to put that all together. So this is showing the sea surface temperature, so the temperature of the top of the ocean. And here you see this red stream coming up from Florida along the East Coast, and that's this warm Gulf Stream current that comes up and hits these cold blue Arctic waters that come down from the Labrador Current around the tip of Canada here. And so this is really what we mean when we talk about climate models. So in this case, I've shown you what an ocean model looks like. So that's part of the climate model. But then we'll also have a climate model for the atmosphere or an atmospheric model. And then we might also have a model for ice sheets, so like Greenland and Antarctica. And then we might even have more complicated things like a forest model on land, because you have to know how the forests and the trees are going to respond to climate change. And when you put all those things together, you get a climate model that can make predictions like these that I showed earlier. But the issue here is that we have to know, if we want to trust these models, we have to know that they're doing something correctly. We have to be able to test them somehow. So the way we do that is we actually make measurements of the ocean. And so I'm going to show you a few of the different ways that we make measurements of the ocean, including some of the ways that I've done it personally. And so this is a picture taken just off the coast of Woods Hole, Massachusetts, one of the institutions that Jesse mentioned I work at. And this is a boat called the RV Corwith Kramer, which is a research vessel. It's a tall sailboat. And right now it doesn't have its sails up, but when there's a lot of wind, we would put the sails up. And this is a boat that I went on last year for a 10-day expedition off the coast of the US East Coast, where we were looking at a current that runs right along the coast. And so this is what it looks like to make a measurement on the ship. This is me reaching over to grab what we call a rosette. So this is about 18 different bottles of, well, they start out empty, you drop them into the water, and then you close the bottles underwater to capture water from that specific region. And we bring it back on deck, we take it into our lab, and then we can analyze the samples to learn things about the temperature, how much salt's in the water, how many nutrients, and we can even look at things like the acidity of the water, which is definitely going to change with climate change. And then you can also do things like look at the species that are in the water. Okay, so that's one of the ways that we measure the ocean. But, you know, it looks like we're working pretty hard here, but we also know how to have fun on these boats. So this is out in the ocean. There's about 3,000 feet of water below us. So this is, you know, this is like the biggest pool you'll ever swim in out in the middle of the ocean. And we took a little break and all went for a swim. And if you look down, it's just completely black because the ocean goes forever. And so we use these methods to study big currents. We have to test our models and make sure that they can represent these large you know, currents that go all the way along the US East Coast. But we also have to make sure that they can represent small currents and that generally we get all of the physics right. So this is me and my friend Raphael in a tiny little river which displays this one type of current that basically the actual physics of the current, it doesn't matter what the size of it is. So a current as small as this, which we can actually go walk in and take direct measurements of, it can function the same way as a current, you know, that's 10 miles wide or something. And so this is another way that we take measurements. Here we're literally just using a ruler and a stopwatch to measure the speed of the current and its depth. If you want to take a global picture, one of the best ways that we can get measurements is to go from space. So this is a video taken by an astronaut, not me, unfortunately, but an astronaut aboard the International Space Station, far above the surface of the planet. And you can see that they can see the ocean. These are clouds. This is land. And if you put instruments on the satellite that take really detailed measurements of the ocean, you can actually get things like the ocean speed, its temperature, how much salt's at the surface. So you can tell a lot about the ocean from space using satellites or measurements even from pictures like this. The one thing about satellite measurements is that they can only see the surface of the ocean. So if you want to learn something about the deep ocean, which is what I study, you have to go out on a boat and actually measure the bottom that way. And what we do, especially at places like MIT, where we're a technical school, we do a lot of math. So this is just, I took a picture of our whiteboard where we were doing some math. So we were manipulating some equations to try and understand the currents at the bottom of the ocean. And the way we do this is we try and simplify the currents so that it's as simple as possible. We say, okay, instead of having a really complicated patterns of winds, let's just assume that the winds were a really smooth shape, and let's assume that the ocean was shaped like a bathtub, and let's assume a bunch of things are really simple. And if you make it simple enough, you can actually solve them on a blackboard like this. And we do a lot of that here at MIT. The other thing you can do is, if it's maybe a little too complicated to solve directly with equations, you can try and recreate the ocean physics in your lab. So here, so I want you to notice this bucket here. So this is a table with a tank full of water. In the center, we put ice. So this is sort of to represent the Arctic, where you have sea ice and really cold temperatures. And out here, we have a warm bath of warm water. So this is sort of like the tropics. And so what's happening is you have a difference in temperatures between the Arctic, this ice bucket, and this warm bath, the tropics. And where I'm at Boston right now, and most of the US, is sort of in this in-between region. And so by what we do to actually get the currents to show up is we start rotating this tank slowly. So you can see this bucket is moving. That's because we're right now looking at this bucket with a camera that's rotating with the bucket, with the tank. And so this is actually rotating, and you can see that these swirls, these swirly currents start to develop. And that's because of both the rotation, so you can think about that as the rotation of the Earth, and the difference in temperatures between the Arctic and the tropics. And we can, using this kind of video, we can make really detailed analyses of the currents, which we use dyes to represent here. So blue current is swirling around this way, this red one is swirling here. And then we have these dots, which are tracing the individual filaments of the current. And by using, again, some pretty advanced computer algorithms, we can actually get the speed of the water by looking at how fast these black dots move over the course of this movie. All right. So what do these climate models tell us about ocean currents in the future? So I showed you something about temperatures in the future, but what if we want to know how the ocean currents are going to change? So this is just a really quick figure from a paper I really liked that came out last year, this nice analysis. So what they showed here is that so there's two scenarios here. In the first scenario, or in the second scenario, where we keep burning gas, oil, and coal, and we keep eating beef, all of these activities emit greenhouse gases into the atmosphere. In that case, the current is going to start out sort of like this, where it stays at about the same strength. Sorry, so again, X here is year, so you're increasing from 1800 to the year 3000. And on the y-axis here is the strength of the current, where 0 would mean the current has completely collapsed. A value of 5 or 6 would mean that it's mostly collapsed, and 15 is where it's sort of a healthy current, and it's as strong as it's always been. And so if we start in the year 2000 and we burn all the gas, oil, and coal and put a bunch of greenhouse gases in the atmosphere, the strength of the current is going to collapse. Over the course of 200 years or so, it's going to reduce in magnitude by about 75%. So most of the current will be gone. And that's really important because the current is part of what keeps, it brings nutrients to the surface for organisms at the surface of the ocean. It takes up CO2. There's a lot of reasons that we want this current to be very healthy. And then this second scenario, which is sort of the environmentally friendly or climate action scenario where we transition away from gas, oil, and coal, and we transition to renewable energy technology, so things like solar panels, wind turbines, hydro power, so dams in mountains, and nuclear, and also to plant-based diets. So instead of eating beef, which burps up a lot of methane, which is a greenhouse gas, and we transition to more plant-based diets, we can reduce greenhouse gases a lot that way. So if we do all of those things and we follow this scenario 1, we can get a little bit of the collapse of the current, but over time it's going to recover and it's going to stay at this pretty healthy value, maybe decrease by about 20% relative to the year 1800. And so this is really the kind of framework that we use to think about how ocean currents are going to change. So we use these computer models, and we'll take 2 versions of the computer model. In one of them, we stop emitting greenhouse gases. In the other, we don't, and we look at how the current changes in both. And you can do a lot of cool work to connect how these currents change to other things. So, if you wanted to look at how nutrients change in the ocean, or how the global temperatures change depending on the current, you can look at those connections as well. So I think I'll stop there for now. I have a few more slides if people want to see them. Otherwise, I'm happy to take some questions.
Great. Thank you so much, Henry. So yeah, guys, we're going to dive into questions. If you guys have any questions on climate, on currents, on anything that Henry talked about, please let's dive in. A few questions, a few teachers will have to demute their own mic. So Ms. Rendine, we'll start with you guys actually. You'll just need to come up and demute your own mic because on my screen it shows you guys as being demuted, but you're not. So come on up, and once you guys do that, we'll take a question. There's already a few hands up, which is great. So, oh, sorry, how to do that? Top of your screen, little microphone symbol. And if you click that, you're good. Perfect. You're good. Perfect.
So make sure it's on topic, okay? So how about JDL in the back? You want to come up a little bit further, closer, so you can, he's just going to come up a little closer.
Yeah, no, take your time.
Quickly. All right. There he is. This is JDL.
Hello.
What kind of question you have?
I have a question.
Yeah, talk loud.
I have a question.
Okay,
Yep.
go for it.
If we just keep on going on the track and not like a normal, and we could keep on going on our normal current, will it go down or will it just stay straight?
Yeah. So if we are able to keep greenhouse gases, so if we don't, if we keep our current at its current levels, or the normal levels, and so we stop emitting greenhouse gases, we're pretty confident, we're pretty sure that we can stop the current from collapsing and keep it pretty healthy.
Awesome.
It will probably decrease a little bit, but we can keep away most of the impact.
Yeah. And so I want to dive into this current a little bit with you, Henry, just before we go to our second question. So can you give us an example of how the current brings warmth to certain places that otherwise wouldn't have that warmth? Like,
sure.
Yeah.
Yeah. So what the current really does is that it takes water from the Arctic and Antarctica. So these are really cold places in the planet. The water sinks there, and then it comes at deep in the ocean. It comes towards the equator, towards the tropics where it's really warm, and there it comes up, and then so basically it's transporting heat from the tropics, which are really warm, to the equator. And so we think that so basically that's one of the reasons that places like Boston and places like Europe and the northeast of the US and Europe are warmer than they would be otherwise. So if you collapse the current, you might cool down some of those places. It turns out that cooling effect in Europe and in the US is actually going to be weaker than greenhouse gases. So there's some offset there. So in the end, you're still going to get global warming. You're still going to warm everywhere. It just might slightly slow the warming in Europe. The bigger thing, rather than heat that it transports, is that it stores carbon. So most of the carbon that we emit in the atmosphere, I think about 40 to 80% of it, so a lot of it, goes into the deep ocean. And so if that current, and the current is what takes it into the deep ocean. So if you shut down that current, all of that carbon dioxide that we emit is just going to stay in the atmosphere, and it's going to sort of accelerate global warming. So global warming would happen faster. So we really want that current to be healthy.
Great. Thanks, Henry. That was great. All right, Miss Caesar's class, if you guys have a question, come on up. You're good to go. Hey.
On the thing, it says you play Fortnite and you teach about this stuff. And I was just wondering, why do you do that?
Yeah, sure. So I'm not playing Fortnite anymore. I've moved on to other games like Civilization 6, if you've heard of that. But the reason I did that is because I was playing Fortnite anyways, and I like to play video games. I've always played video games. But I'm also getting further in my career where playing video games is maybe not the best use of my time. And so I wanted to sort of combine my work that I do during the day and playing video games, which I usually do after work. And so I started this Twitch stream where I would play Fortnite and talk about climate change with other guests in my squad, or also just random people I would play with online. And so for me, it served two purposes. One, it was really fun. And two, it was a way of educating mostly younger people who play video games about climate change. Because the thing about climate change is that it doesn't matter that much for old people because they're not going to experience the really bad impacts. But for people like me and people younger than me, it really matters because you're going to be living this with for the rest of your lives. So, yeah.
Awesome. I was wondering how long it was going to take for that question to come up without me saying it at the beginning, and it was literally the second question. So thank you. All right, Miss Fletcher's class. Come on up, guys.
Why do rocks break during climate change?
Can you repeat that?
Yeah.
Why do rocks break during climate change?
Rocks?
Yes.
Yeah. So I think I know what you're talking about. So one thing that happens with climate change is that as we put carbon dioxide in the atmosphere, you're going to warm the planet. And so some rocks will actually just break because it gets so hot. So for example, in Yosemite, the summer is getting so warm that some of the cliffs are actually cracking due to the heat. So that's one reason. The other reason, and this takes a much longer time, is that as you put carbon dioxide in the atmosphere, you make the rain more acidic, so you get acid rain. And the acid rain can actually weather away, and it sort of dissolves the rock over time. And so you can break rocks that way. It's sort of a less exciting, fracture. It's sort of a slow wearing down of the rocks.
Excellent. All right. Mr. Gohar, so I know you guys typed in a question on YouTube, but you can pass along one here. But like Ms. Randin's class, you do need to demute your own mic. Because for some reason, it's a little iffy on mine. But yeah, so if you come up, little microphone symbol at the top, click that, and we can take a question directly from you guys, which is better. And there you go. Yeah, you should be good to go.
All right. So our original question was about the Fortnite thing, because, again, that's one of our main connection pieces to kind of that whole thing. My kids all play Fortnite and stuff, so they're very excited about hearing that a scientist plays Fortnite. How does playing video games correlate to climate change? You know what I mean? Like we know why you played Fortnite, because I mean, obviously you were getting out your message to a mass amount of people because of the high interest in that area. What about optimization? Is there a way to kind of role play climate change within those video games to kind of model what's going on and what doesn't change?
Yeah, absolutely. So that's actually one of the things I'm really excited about. So the reason I switched away from Fortnite and towards this other game called Civilization 6. So in that game, they actually, in the new expansion, they built climate change into it. So now as you develop your civilization in the game, as you start, driving trucks around and flying planes, you change the ecosystem, the environment in the game. And then there's this whole like geopolitical system. So there's other countries that you're playing with. And if only one of them is emitting the greenhouse gases, but then it impacts the other, then you have to sort of work together, with another player, another person around the world online. You have to work with them to solve climate change. And the really exciting thing there is that these games only take 1 hour, but you really can experience what it's like to try and solve the problem of climate change in a really fast-paced, interactive way. And the only other way to do that is to just go through it, you know, over the next 50 years and actually experience it in real life. So having these ways of simulating the kinds of challenges we have to deal with is, I mean, that's really exciting. And that's sort of why my project moved away from Fortnite when I realized there are these other games that had climate change built into them a little bit more.
Awesome. Great question. Great answer, guys. All right, Miss Curtin's class, if you guys have one.
Yeah.
How did it start?
How did what start?
The currents.
What causes the currents? What makes the currents?
Yeah, that's a great question. So there's two parts to that. So one is that the currents are drawn up by winds in the Southern Ocean. So around Antarctica, you have these really strong winds, the strongest winds on the planet. They're almost as strong as a hurricane, but they're like year round. And these winds just push the water so hard that it actually brings water up, and that's what generates the current. So that's one part of it. The other part is that at the bottom of the ocean, and this is now the part that I'm studying now, this is where you have a lot of this mixing. So you have these waves that are really turbulent. They're like moving water around like crazy, and that actually gives energy to the currents, and it drives them that way too. So depending on the part of the world and the part of the ocean, the part of the current that you're thinking about, they might have different forces that cause them. And so we try and work together some kind of combined theory for how the whole global current works. So we're still working on that. We have a lot of the pieces so far.
Awesome. And then just as you got started, we had our final class join us. So Miss Van Wyck's class from Toronto grade 6s. If you guys have a question, come on up. And you should, oh, you muted yourself. You're good. Yeah.
All right, we have a question from Nathan.
All right, so I was wondering what's in the water that like carries electricity?
Like, how do you get power on the boat?
Yeah.
Yeah.
So on the boat, we have a generator. So I think we burn gas to power the generator. So we make our own electricity on the boat, which is not great, right? Because we're contributing to climate change. We're making it worse by burning the oil. So they're actually working on other technologies to power these ships. So that's how we get electricity there. But then the other part and the more challenging part is that sometimes we want to do things far away from the boat or far away from land. And so one thing that we've been doing a lot in the last 10 years is building robots to go to parts of the ocean that humans can't go. So if you want to go to the bottom of the ocean, it's really, really, really expensive to build a submarine and make humans go there. But you can do it for, you know, maybe $100,000, which in comparison is really cheap. And you can send a robot to anywhere in the ocean you want, but then you have to power the robot. And you can't just hook a wire to it because the ocean's so big. So you have to give it a battery. And so there we've been really trying to develop better batteries, which can keep these robots powered for longer and longer. And so the best we have right now are robots that can last about 10 years in the ocean without ever being recharged. And they like send their data back to satellites every week.
Super cool. All right, guys, we were ripping through these, so let's do a whole other round of questions. Ms. Randine's class, if you guys want to start, just come on up and demute that mic, and you're good to go for number 2.
Aaron, go for it.
My question is, does the moon have anything to do with like global warming and like how the ocean moves?
Yeah.
Yeah. So it doesn't directly have to do with global warming, but it does change the currents, and so through the currents, it indirectly changes global warming. So you're right on, actually. So the mixing I talked about, this really vigorous moving around of the currents that happens at the bottom of the ocean, and actually what I'm working on for my PhD at MIT is almost all powered by the moon. So the moon and the sun, when they orbit around, well, the moon orbits around the Earth, and then the Earth and moon orbit around the sun, and as they go through those orbits, they pull on different parts of the ocean at different angles. And so you actually get a tide. So you get this really big current that sort of sloshes over mountains. And that sloshing over the underwater mountains causes mixing and gives energy to the currents. And that's a connection that we really don't understand super well yet. And so that's what I'm working on for my PhD, is to understand exactly how the moon is giving energy to these currents and exactly how much energy they give and how much energy they might give in the future. Those are really interesting and important questions.
Awesome. We're getting a lot of really diverse questions today, so thanks to all the classes and students. You guys are awesome. Miss Caesar's class, come on back up. If you have a second.
We do. Hold on.
You do. That's okay. Take it down. All good.
When you were our age, is this the job you thought you would be doing?
Good question.
Ooh. So when I was in middle school, I took a earth science class where we learned about earthquakes and volcanoes. And so at the time, I thought I wanted to study volcanoes in Hawaii, also because Hawaii is beautiful. And so I wanted to go there. And also I grew up in San Francisco, California, where we have some of the worst earthquakes in the US. And famously in 1906, we had this terrible earthquake that just completely, it like burned down all of San Francisco. So growing up, we were always sort of worried when the next one was going to hit. And so that's what got me my initial interest in earth science. And then I went to college and I studied math. And then I sort of forgot about earth science and oceanography until I took a class my last year of college about oceanography. And I learned that you could do the stuff I do now, which is studying ocean currents and how they affect climate. I fell in love with it as soon as I saw it, and I've been working on that for the last 5 years.
Very cool. You touched upon a point I always like when we do with scientists, and that is that like this is not your goal and passion from when you were like 2 years old all the way along. One of the other things we get from a lot of students is this idea that scientists have to be really, really smart in all things from when they're a really little kid. And you might have been, but I'm curious if you had any experiences where things didn't go your way in school or things were difficult for you, because that's always nice to share if so.
Yeah, I was always pretty good at math specifically, not very good at anything else, it turns out. Like English and philosophy and geography, and especially the humanities and the social sciences I was not very good at, not very interested in. And yeah, so I just sort of kept doing math mostly because it was good at, not because it was what I loved. And then I started, I took this oceanography class and realized that that was a way I could apply the one thing I was really good at, math, to something that sort of mattered more on a personal level.
Yeah, thanks. That's awesome.
Yeah, and also I should say that, so I'm at MIT now, which is like a pretty famous school for really strong science and technology. I didn't even bother applying for college because for undergraduate, because I knew I wouldn't get in. And so I worked really, really hard in college to get good enough grades that I could come here as a graduate student and do a PhD.
Way to go. Yeah, again, worth noting for the classes, like MIT is one of the elite schools in the entire United States, and in fact, the entire world. So kudos to you, Henry, for putting in the work and getting there. Way to go. All right, Miss Fletcher's class. You guys have oh, I got you. Yeah, you're good to go.
Okay, go ahead.
What happens if you get to the top of the chart that you last showed us?
The top of the chart?
Yeah.
What would happen like to the earth and the animals and things like that?
You mean it for the temperature, if the temperature went all the way up to the top of the chart?
Yes.
Yeah. So that chart I showed was for the global temperature. And it showed that the global temperature would increase by 3.5 degrees Celsius. That's about 6 degrees Fahrenheit. That maybe sounds like a lot, maybe it doesn't. The important thing to notice is that that's the global average. And the Earth is not warming the same rate everywhere. So somewhere like San Francisco might warm at about that rate, but somewhere like Alaska is going to warm much faster than that, probably 2 to 3 times as much. So there you could get a change in your average temperature. Just if you went out on an average day, it might be up to 15 degrees Fahrenheit warmer, and that's a lot. That's when your winter starts shrinking, you get more melting. The ground, if it's frozen most of the year, is going to start thawing, and you'll get permafrost melt. You'll have sea level rise and things like that. And so actually that's a really good point, because the global picture doesn't look that bad. It's when you start looking at like individual places and the impacts there, that's when those numbers get pretty scary. And so that's why we really have to make sure we avoid those really big impacts and get serious about changing climate now and really transitioning away from these dirty energy sources.
Yeah. We did another climate change hangout earlier today, and it's really interesting noting that like 1 degree is all we've gone up so far. And Henry, in your and I's lifetime and in the teacher's lifetime, we will have seen this massive change in weather patterns and storms. You know, once every 100-year storms happen every single year now, hurricanes, droughts, floods. For kids, you'll start seeing this in the next few years. You might already have started seeing it, that weather's changing as a result of this very minor temperature change. So if it increases even more, we'll get bigger impacts. Great question. Mr. Gohar, again, if you guys want to demute, come on up for a second question. And your students, if they want to be equally excited about being on camera as they were last time, that's awesome. And you're good to go, yeah.
Hi, guys. All right, Max.
What got you interested in climate?
Yeah, so I got interested in climate actually through oceanography. So I was really interested in the ocean and the ocean currents. And then I realized that the reason that most people today care about the ocean currents is because of climate, because they're so important for transporting things around, for taking up carbon from the atmosphere. And so I really wasn't that interested in it at the beginning. And now, since I've been studying in this climate science program, and my roommates are all climate scientists, now I'm learning more and more about the whole climate system rather than just the oceans.
Very cool. All right, Miss Curtin's class, for our second last question of the day. Come on up, guys.
Why does water from the ground evaporate as rain, but why doesn't salt water evaporate?
Yeah, so salt water does actually evaporate. And so most of the rain that you experience, you know, so there's a lot of rain over the ocean, and that water comes from the ocean, it evaporates. So just because there's salt in the ocean doesn't mean it can't evaporate. Yeah, and then on land, it might be counterintuitive, but you actually can get a lot of evaporation from plants. And so plants will have a lot of water in them and in the soils, and you can get a lot of evaporation out of those. So that's why, for example, the Amazon rainforest, a lot of that rain is just recycled through the plants and the rain, and then it keeps, you know, it rains and then it evaporates again, and it rains and it keeps doing that cycle.
Just a quick follow-up, as we've had this question before about salt water evaporating. So when it evaporates, though, does it take the salt with it, or does it come down as just fresh water?
Yeah, good point. So when it evaporates, it leaves the salt behind. And actually, you can look at how salty the water is on the planet, and you can actually basically see where the raining is happening because it leaves all the salt there, and you have more salt in certain regions than others. And actually, one of my friends here, for his PhD, he spent 5 years studying how the salt patterns in the ocean are going to change, and then trying to relate that to changes in rain. Because it turns out it's really hard to measure changes in rain. It's really easy to measure changes in salt. So that's actually, you can sort of exploit that relationship to learn more about the system.
Very cool. And then to wrap up with one last question, Ms. Van Wyck's class, come on up.
Hi. Hi. Where do you go to, what locations do you go to study like climate change and the ocean?
Yeah, so most of the work I've done so far, except for that little cruise we went off the coast, most of what I study so far is using computers and using data that someone else collected. But I'm really excited. In a year, I'm going to go to a current off the coast of Ireland, and we're going to go for 40 days on a ship and measure the currents there. So I'm really excited for that. That'll be my first time on like a really big research boat, out in the deep ocean. But that project is sort of more about the current rather than the climate. But you can really study climate anywhere. I mean, climate is going to change anywhere. One of the places I'm really excited about is Antarctica, because that's one of the places where the most change is happening. You have a lot of ice. A lot of it's going to melt as the temperatures warm. And so I'm like really hoping that in the next few years I'll be able to go to Antarctica. And I have some friends who have gone, so I'm hoping that I'll be one of the next ones. Yeah.
Fingers crossed, man. Good luck. Henry, before we wrap up, I always like to ask the question, is there anything else that you want to share with classes about where they can learn more about climate research, about the work that you're doing, about ocean currents in general, anywhere we can point the classes to?
Yeah, sure. I think probably the best resource that I really like is NASA's websites. If you just look up, like Google NASA climate, they have a lot of really great information and movies and videos. Like that movie I showed of the Earth from an astronaut, that was from NASA. They just have a lot of the best information, I think. And, NASA is an amazing organization, and happy to be an American.
Outstanding. Thanks, Henry. That's great. Well, we do at the end of every hangout, I'm going to demute every class's microphone. And Miss Curtin's class, yes, you can get a picture with Henry at the end. But for now, I'm going to demute everyone's mic. If you guys could join me in saying a huge thank you to Henry for joining us today. Everyone is demuted. Go right ahead. Thank you so much.
Bye. Say bye.
Thanks, everyone.
You got louder. Thank you guys so much. We look forward to having you back soon. Henry, thanks so much for joining us tonight. Henry, do stick around. We'll picture with you with one of us. But for now,